Hello, and welcome to our first lecture for analytical chemistry. So today we will be mostly dealing with how we deal with numbers. We will talk about metric system. We'll talk about significant figures, and we will talk about ways of calculating the concentration of things. So let's start with the metric system. All right. So the metric system. The metric system is this awesome system that essentially allows us to give certain aspects of nature a quantity. And by aspects of nature, think about everything that you would want to or you could think of measuring. And we have a unit for each of these things. Now, the metric system is directly, or I wouldn't say directly in competition, but I guess we could compare it, which was with what's known as the imperial system, which is the system of measure that we here in America use. In fact, we are one of the only people, we are the only countries in the world that actually use the imperial system. Funny enough, the imperial system of measure is actually directly based on the metric system. So every sort of imperial measure that we use has to first be calculated on its metric equivalent. So in a way, the imperial system, not only in my opinion, is somewhat not useful compared to the metric system, it does not make sense to use such a system when that system itself draws all of its values from another system which is arguably superior. So the metric system defines these units of quantity as the following. So we could look at the mass of something. So by the mass of something, when you step on the scale, you get your weight. Now, weight and mass are two separate concepts. Because think about it. Let's say you were to step on a scale in space. The scale would read 0 because there's no gravity to force you down onto it, and therefore it would say that you weigh nothing, which would technically be true, but you would still have mass associated with you. Mass is an unchanging concept or an unchanging quantity, meaning that no matter where we go in the universe, the mass of the object would be conserved. Conservation of mass is a very important aspect in chemistry. We can't just magically gain or lose mass. It has to come from somewhere or go to something else. So, no matter if we're on Earth, space, the moon, anywhere in the universe, we would have the same mass but different weights. It just so happens that on Earth, our mass and our weight are one in one with one another. Our systems of measure are designed as such to make this nice thing occur. So, an interesting question that isn't necessarily chemistry based, and one that you may be asked in somewhat of an advanced physics class is: how would you determine the mass of an object in space? And the answer to such question would be using a spring, because if you take an object, place it on a spring, and then pull the spring and release, it's going to oscillate on that spring in relation to its mass. So the more or less the object weighs, the faster or slower the object will vibrate on this spring. So none of this is important for this class. I just wanted to sort of how should I put this? Tie together the difference between mass and weight and how they are similar but not the same. So mass is actually our first unit of measure on the metric system that I would like to present, and it would be represented by a unit known as the kilogram. The next unit that I want to talk about in that unit quantity is length. After length, we have time. Let's see. After time, we have electric current. And we have temperature. We have the amount of something. And finally, we have what's known as luminous intensity. So each of these also has its own base unit for their quantity. So for length, we have what's known as the meter, which is represented by a little m. For time, we have what's known as the second, which is represented by a little s. For electric current, we have what's known as the ampere, which is represented by big A. For temperature, we have what's known as the Kelvin, which is represented by big K. I will note, though, chemistry, although we do use the Kelvin quite a bit, we will also use centigrade or Celsius a lot as well. So just keep that in mind. Although Celsius is not technically the proper metric unit for the temperature in the metric system, we still use Celsius a lot in chemistry. The next unit is, well, for the amount of substance, and for all chemists, this should be a common concept, and it is known as the mole, and that is also known as Avogadro's number. And finally, we have luminous intensity. And while luminous intensity is essentially the amount of light something gives off, and in some matters of speaking, you could think about it as the amount of photons that are being given off by an object, since light is essentially what photons are, or light is made up of photons. So for luminous intensity, we have what's known as the candela, which is represented by CD. Now, all of these quantities right here and measures make up pretty much all the measurables that we have in our universe. There are no other measurables, at least speaking in the terms of a single unit, other than these. We have mass, length, time, electric current, temperature, the amount of a substance, and luminous intensity. So, these units are not the whole picture of the metric system, and they're not what truly make the metric system such an awesome system. It's the prefixes that the metric system come built with. So let's add these. Let's go with prefix. After prefix, let's say symbol. Symbol, let's say power, because there's a way to use exponents here. And then let's talk about the decimal equivalent. Now, this list I give you right here is by no means a complete exhaustive list. They're just some of the most common prefixes that we First prefix is giga. The next would be mega. Then kilo. And after kilo, this is where I would set what is known as the base unit. So let's say this is base. And by base, I mean it is the number with no prefix at all, or it is the unit with no prefix at all added. So it's not being manipulated in any way. After or below kilo and below the base, we have deci. After deci, we have centi. After centi, we have milli. Then micro. We have nano. And finally, pico. Now, I can't recall if we get smaller than pico. Probably do. But for our purposes, we're not really concerned with it. We're probably not even concerned with anything as small as pico, to be honest. I have this chart much more nicely drawn. Read over. Oh, that's so much nicer. Fix some things. So the power right here would be the 9th, and to the 6th, 3rd, and to the negative 1st, and to the negative 2nd, negative 3rd, and to the negative 6th, and to the 9th, and 10, negative. These are all the prefixes we're really concerned at. So, what these prefixes mean are the following. For instance, let's look at meters, for instance. If we had 1 kilometer, or kilometer, that would mean that, so we have that kilo and then meter. That kilo essentially means 1,000. 1,000 meters. For instance, if we had 1 kilogram, kilo, we have gram, 1,000 grams. Now let's look at centi, for instance. So centi is equal to, well, centi is equal to 10 to the negative 2. It is also, we could interpret that 10 to the negative 2 as 1 over 10 squared. And that would mean that that is 1 over 100, which is also equivalent to 100th, which is 0.01. So what does that mean? Well, that would mean if, for instance, if we had 1 centimeter, we would have 1 100th one 100th of a meter. And this 1 100th essentially is the same as 1 over 100, or 0.01 meters. So all these prefixes are doing is they're being equivalent to one of these essentially decimal equivalents, and also these power equivalents. So as long as you have memorized, which I highly suggest you all do, As long as you have these prefixes memorized, whenever we see any of these terms listed, we immediately know how to convert to any of these other units in the system. Now, one of the really nice things about the metric system is that ability to convert between units. So, let's say we measure something on the scale and it was 0.001 grams. We could represent it like that, but we could also represent it as, well, how many decimal places to the right is that 1? So if we went 1, 2, 3, and we made it 1, we would see, well, if we go 3 to the right, we have milli, which is 10 to the negative third. And milli is equivalent to, well, we put this milli right here, 1 milli gram. So just like that, I went from 0.001 grams to 1 milligram just by moving the decimal 3 points to the right. If you know the equivalent for the unit, you essentially will be able to convert any of these. And that's really the true power of the metric system. Once you have these prefixes memorized and the powers associated with them, you can pretty much convert between the two units or any of the units in your head quite quickly. Now, I want to make a few more notes on this. If we look at these units or these quantities of measure, we see that length is the meter, time is the second, amount of substance is the mole. But one of the base units is a little strange, and that's the kilogram. The kilogram, you would think, why would it not be referred to as just the gram? Why wouldn't we use the gram as the base unit for weight? And the reason is sort of funny, and it is because the gram is a very small amount. So it's very difficult to measure a very small amount very accurately. It's easier to measure a larger amount than a smaller amount of something. Especially back 100 years ago, 100 plus years ago, when these units were essentially founded and came to be. Another interesting point is, well, the unit of mass, the unit of length, and several of the other units, I believe, were all based on some physical construct in nature. And by that I mean the mass of a kilogram used to be based upon a platinum cylinder that was stored in a specific vault in Paris. This cylinder was said to be equivalent to exactly 1 kilogram. No more, no less. 1 with an infinite amount of zeros to the right. So it was defined. It was the kilogram. And everything else in the world was based upon this kilogram. In fact, this original kilogram had several copies of it made, and these copies were shipped to the other countries in the world, including America. And I believe every year or every several years, there would be a point where all of these copies would be brought together for a weighing to see how much they changed from one another. As you can imagine, one of the issues with using some physical construct like a cylinder in nature, it's a poor choice to use because, well, it could lose or gain mass depending on the atmospheric conditions, depending on if there's some other substances around it. It's not going to maintain its mass. That's the main idea here. And because it's not going to maintain its mass, and because that mass is going to fluctuate over time, it is not what could be considered a reliable source for something like a unit in the metric system. And as a result, and it's sort of funny enough, when these masses were brought together and weighed against one another, we indeed did see them fluctuating from each other. Some would get heavier, some would get lighter, some would bounce around between getting heavier and lighter between each weigh-in. There was no consistency between them. So actually, I believe only a few years ago, we redefined what the mass essentially is. And we redefined it, instead of by using a cylinder in some vault, or how should I say this? We used the electromagnetic constant of the universe and equated mass to that using this very interesting machine known as the Watt balance. This balance essentially employs an electromagnet that pulls on a scale, and it will pull on a scale using a specific amount of electric current, and as a result, we can equate the electric current of something to its mass. And through a bunch of um, very nasty equations, you'll see that we actually can do that. And what this balance does is we now have a value for the kilogram that will never change. Just like in reality, no matter where we go in the universe, we never gain or lose mass in the sense that it has to essentially be taken from one spot and moved to another. We can't just magically gain or lose mass. This new definition of the kilogram no longer magically gains or loses mass. It will remain constant everywhere in the universe, no matter where it's essentially set up. So, in the same way that we redefine the mass, we also redefine the length, because also interesting enough, there was another piece of metal in this vault in Paris, and it was a platinum bar. And the platinum bar was a specific length of, probably guessed it, 1 meter. And this bar was what we used to use to define how long a meter is. However, more recently, we redefined meter as the distance light travels in 1 second. So light is a universal constant that will never ever change in speed, no matter where it's measured in the entire universe. And as a result, no matter where we measure it, it will always give us the exact same amount for the meter. So we now essentially have two of these constants that are defined by unchanging variables in the universe. The time constant, I believe, is calculated by the rate of which I can't remember specifically. It was either the frequency at which a specific type of star pulses, or it was the decay of a specific isotope of a specific element, because both of these things actually keep time insanely well. You've probably heard of an atomic clock before. An atomic clock works by measuring the rate at which a specific isotope of an element will decay into another element, and this time is actually incredibly precise. It is very constant, and as a result, atomic clocks are able to keep time without losing seconds to an extraordinary level of precision. Um, the electric current, I'm not sure I can't remember what it's defined as. Not entirely sure on temperature, and I'm not entirely sure on luminous intensity. The mole is I believe it is a mathematically calculated value. However, there might be, I cannot recall, but there might be a similar instrument to the Watt balance, which relates the molar mass of a substance to, or the moles of something to some other fundamental concept. I do remember that one of the competing ideas to redefine the mass was this. I cannot remember the material, but they were trying to make this perfect sphere, and I can't remember the material it was made out of, but it would essentially equate the mass of an object with the moles of what the material was made out of. In my opinion, I think that was a not the greatest idea, because again, we're defining a constant based on some physical object in our universe. But then again, who knows? We use the Watt balance, so that's how things are so far. But I think that's all I really wanted to talk about with the metric system. Main point I wanted to get across is the metric system is cool. You should probably use it whenever you can, and definitely make sure you memorize the prefixes on here, because that will definitely make things so much easier. The next thing I want to talk about is significant figures. So I assume most of you have heard or used significant figures at some point. I also want to state that pretty much everything in this class will be essentially based on significant figures. We want all of our results in any calculation we perform to have the appropriate number of significant figures in the answer. So make sure whenever you're doing any calculation, whether it be in lab or lecture, that we account for significant figures. So I'm going to go over all the rules of significant figures and why we use them. So, all right. Awesome. So a traditional example would essentially be we're given two objects with two different rulers and we're measuring them with the rulers. Both of these objects are a pencil and both of these pencils are the exact same length. But as you will find out is both of these rulers, although they both are decent rulers, and their major tick marks, the 5, the 6, 7, 8, 9, and 10, all occur in the same exact spot, we will get two different measures for this pencil based on this ruler. So this type of measurement is known as analog measurement. So analog measurement is essentially a measurement that you have to perform. For instance, if you have a ruler, you have to look at the ruler, identify the tick marks, and conclude a measurement. Thermometer that is not digital, meaning one that does not have digits that occur on it. One that you have to look at it and observe the tick marks and make a reasonable assumption on the measurement based on those tick marks. These are analog measurements. Analog measurements are ones that we have to make what is known as the assumption. And I will go over what that is right now. So when we look at this first pencil, we see that its tip falls between 7 and 8. I'm sure we could all agree that between 7 and 8 is a very good estimation for where this tip falls in. But we could do even better than 7 and 8. Because we have these minor tick marks here, we know that 1, 2, 3, 4, 5, 6, 7, 8, 9. We know even better than 7 and 8 that our line falls between 7.8 and 7.9. Now, at this point, our ruler is no longer able to give us any more digits. We know for certain that this tick mark is between the 7.8 and the 7.9, but other than that, we don't know anything else. So before we could actually conclude this measurement, we have to make what's known as an assumption or a guess on the last digit. Any digit in any measurement made is always a guess. Even on the digital instruments, which I'll go over in a moment, the last digit this digital instrument gives you is not an accurate measure. It is a guess that the instrument makes based on a set of criteria, which we will talk about. So at this point, we need to make a guess. We need to say that this number essentially has to be 7.8 something. And so this guess could be anything we want. We could put a 5 here, we could put a 4, 6, 7, 9, any number between 1 and 9. We could put a 0 if we want, but it has to be a digit. We have to put something. It can't be left blank because the last digit always has to be a assumption. If we left it at 7.8 and someone were to look at it, they would think that that 8 was the assumption, and that would be incorrect because we know for a fact that this pencil is at least 7.8 because it passes the 8 mark. So this is the reason why we need to make a guess for our last digit. And so I would say that this tick mark is much closer to the 7.9 than it is to the 7.8. So I would say 7.89 would probably be a good guess for this last digit. You could, as I said, 7.88 would work, 7.87, anything within reason would work. For this next ruler, we see that the pencil's lead falls between 7 and 8. However, this is all that we see. We have no more minor tick marks to go by, and so we are now left with the following value. We have to put 7 point something for our answer because remember, in the same way that this last value was essentially assigned, our last digit has to be one that is a guess or an estimate. Based on this, I would say 7.9. Or 7.8 also works, 7.7 also works. As long as that last number, that 9 that I selected here, is within reason, it is an acceptable guess. That last digit will always be a guess. The one before that last digit is a definite. We know that the pencil is 100% 7. It could be greater, it could be more than 7, but we don't know how much more than 7. But we know it is at least 7. This is the whole idea behind significant figures. We always want to present our answer to have one more digit than the certain digit. So any number that we measure, any number that we look at in a text or anything, the last digit is always the uncertain digit, and the digit before it is the certain digit. Let us look at a digital instrument now. So a digital instrument would be something like this analytical balance right here. So this analytical balance, we're going to put an imaginary weight on it. So I actually drew this out. So let's actually draw this out. Let's say I take this mass, this little weight, and I place it on the scale. And let's say that the actual mass of this weight is 1.56484. And every digit to the right of that 4 would be a 0 for infinite amount of space. So let's say we use 3 different scales to measure it. Let's say that our first scale has 2 points or 2 decimal points after the 0. Our second scale has 3 and our third scale has 4. So we have 3 different scales that we're going to use here. Now, I'll read this over. When we place this on the scale, when we essentially put this mass on each of these scales, it returns the following digits. Now, I want to actually remove. So we get the following values from this scale. This last term, just like in all of our analog calculations, is uncertain. Note that when we did the analog calculations, we guessed the last term. This instrument, this digital device, is also making the guess, but it's doing it in a slightly different way than we would do it. Not really, but it is. So how should I put this? How should I copy these? I really hope I can copy these. It's awesome. For some reason, OneNote, as of late, has refused to copy any of the things I sketch if there are text in it. Oh, goodness, I was able to pull this down a wee. So let's say let's assign some values. We have 1.55, 1.55 or 560, and 1.55. Let's say this is what this is. So when we put this mass on the scale, this 1.5484 mass on the scale, 1.56484 mass on the scale returns the value of 1.56 to us. And the reason why it returns the value of 1.56 is because when that mass is placed on the scale, it is able to see that the mass is, it's at least 1.5555, but it can't be greater than 1.565. It doesn't know. It knows that the mass lies somewhere inside this red area, but it's unsure exactly. So what this scale actually will do is it will take the middle value. It'll look in the middle of this square and take the exact center value that exists in the absolute bounds of the minimum and maximum value that the scale could possibly measure. And that's why we get this 1.560. This 1.56. This 1.56 is the result of the scale guessing the possible value by taking the midpoint of the range of values that it could actually be. So when we go to the next scale, it's really interesting how this sort of plays out. We get another decimal point of precision in this scale. And so the scale again looks in this blue area because this blue area is essentially what's occurring when we get this new extra decimal point. What's this blue area is saying that we have the range of 1.56 1.5645 and 1.5655. You notice we are essentially moving up by this last, essentially moving up by this much. We're going from this 45 to this 55, so we're jumping by a point in these last decimal places. So this entire area between these two limits are essentially 0.001. Limits of these two lines are 0.01. As you see, we're going from 555 to 565. So from this 55 to 65, we're going up a factor of 10. So, or 0.01. And we're going to see that we also have this range here as 0.0001. And you'll sort of note right here 0, 0, 0, and we see we have 4 spots there. We have 4 spots there. See how we have 3 points of precision here. We have 3 points of precision here, and we have 2 points of precision here, and we have 2 points of precision here. What's happening is as we add on an additional decimal value, we're narrowing in closer and closer and closer on the actual value of this cylinder. Notice how in this second value right here, we get, or in the second scale with 3 decimal points, we get the value of 1.565. 1.565, that last 5 is actually incorrect because we know our actual weight is 564. Just goes to show you how that last digit is a guess. The scale is saying that, well, our number could be in between these two numbers. Let's choose the middle number as the number we're going to go with. That is 1.5650. We know it could be in between these two. However, we're going to take the middle number right here. And as you will see with our third scale, it gives us this green chart. Our value actually lies slightly to the left of that midpoint. And if we look at our first chart, our blue segment lies slightly to the right of the midpoint that it essentially used to make the guesstimate. And so in this last green scale, we will see that we have the values of 1.564 7, shrink this, 1.56475 and 1.56485. So it sees the values in between these two, and what does it do? It takes the middle value, which is 1.5648. So scales are essentially doing the same estimate that we're doing when we look at a ruler or a thermometer, but they're doing it in a slightly different way. The scale is saying that it knows that the value exists in this sort of region. It does not know if the value, where in the region the value exists, but it knows that it exists in that region. And so as a result, it will essentially look at the bounds of that region, divide that bounds by 2, and take that center point, and that's how these scales give you the mass that they give you. Just note that all of these scales, the last digit is always a guess, in the same way the last digit of a thermometer or a ruler is always a guess. And you could see that in our second value. It says that the last digit is a 5, but we know, based on the actual value of this mass, that it is indeed not a 5. So that just goes to show you how scales essentially are providing you that uncertain digit. The next thing we are going to talk about is the addition and subtraction of significant figures. But first, I sort of want to give an idea of why we want to do an addition and subtraction of significant figures. So let's say we had give this crudely drawn image I have here. Let's say these are two boats. And this is a little bit of an overcomplicated, but maybe not, example. Let's say we had two boats and we wanted, and let's say the harborman at a dock wanted to know the length of the two boats to see if they would fit at their dock. So one person measures their boat with a ruler that essentially has minor tick marks and goes from 100 to 400. The other person measures their boat with a ruler that has no minor tick marks, and it goes from 100 to 400 as well. So what happens is the first person essentially measures his boat, and he sees, well, how big is my boat? We have at least 200. It's at least between 200 and 300, but we have minor tick marks as well. So let's say since there are 5 of them or 4 of them, they're going to each represent 200 or 20 points. So 220, 40, 60, 80, and 100. So that bumps us to 300. So 220, 240, we know for a fact that our value exists between 240 and 260, right? So this would be 240 to 260. 2, 4, 6. And what that states is we could be off by up to 40 points. Because think about it, between the 40 and the 6, not 40 points, 20 points. Because the difference between 240 and 260 is 20, that means that there are 20 digits in between this number where we are just totally unsure about in the measure. But we're going to make a guess. Based on where this vote ends, we're going to say this looks very close to 259. So I'm going to say this is 259. The next person measures his boat, and he sees that the boat is between 200 and 300. And at this point, he knows it's between 200 and 300. But this can be off by up to 100. So we could be off by 100 units on this second ruler, and this first ruler could only be off by 20. So as you can see already, this first ruler is already far superior for measuring these boats. So let's say we want to essentially add these two numbers together to see how long both boats are. So let's say both of these people came back to the harborman, gave their measurements, and let's say this person right here gave a measurement of, I don't know, let's say 270. Because remember, we have to guess that second digit. This digit is this first one is certain. This second is uncertain. And this 0 is just a placeholder. We essentially need the 0 there, otherwise it would be 27, which wouldn't make sense. We know that this is in the 100th place, or the 100 place, and we know that this is in the 10 place. So that would mean that we have to have something in the 1's place. So what we're going to do is we're going to add these two numbers together. Let's say this first one is 259. And we're going to add to it 270. Well, we are going to get value for this of 529. That's right. Yep, Correct. So 529 is the value. However, this is not the correct value to the proper significant figures. Because if we were to accept this value, it would say that the 9 is the uncertain digit and the 2 is the certain digit. We would say that the boat is definitely, or the two boats together, are 520. However, I want you guys to look back to the second boat. This second boat is capable of being off by a measurement of 100 units. And in that regard, let's say it was off by 100 units. Would this 20 actually matter? And the answer is no. Because this second measure is off by such, or it's capable of being off by such a large amount, by saying this value, or using the proper significant figure, which would come out to 53, 530, it would say that we have at least 530 feet, or 530 distance total, when that's not the case. We could be off by a factor of 100. So adding this 5.3 is completely and totally, actually, whoops, my mistake. So adding this 2.9 is actually completely and totally pointless. We're saying that this 9 right here is we're definitely able to measure that 9. And that's not, or we're guessing this 9 and we're definitely able to measure this 2. And that's not the case. In fact, we're sort of guessing this 2 and we could definitely measure that 5. And as a result, this 9 has to be removed. This 9 essentially is not an accurate measure. It's saying that the least accurate measure is this 2, when in the true case, it's this 5. So this should come out to essentially 53. Round it. And I'm going to go over exactly the math that we need to do to solve this after that. After this, I just want to sort of explain why we want to use significant figures. And the idea behind it is, if one ruler could be off by a factor of 100, what does it mean to have 20 points of accurate, or this much, to be so much less significantly off by the first ruler? If this first ruler is off by a factor of 100, it completely makes this insignificant. And since that's insignificant, we don't want to portray it as significant, so we need to change or round our answer to reflect our least precise measure. And that's essentially what all the mathematics in significant figures are going to be. We are going to modulate our final answer based upon the number in our maths that is the least significant. So let's go over that right now, actually. So let's say this is counting significant figures. So these are the rules for any number in determining how many significant figures that number has. The first rule states that every number that is not a 0 is a significant. So 1 has one significant figure, 15 has two significant figures, 56 has two significant figures, and 463 has three significant figures. All the numbers are non-zero, so they are all significant. The next rule we could look at is all zeros between two non-zero, and it's important that they're non-zero, numbers are significant. So we will look at our first example. We'll see 10. We'll see that 10 has a 0 in it, therefore it is only one significant figure. It's not being sandwiched between two whole numbers. Instead, it has a 0 at the end. So another way we could put this rule is that trailing zeros without a decimal place are not significant. So this is a 10, so only the 1 is significant, so we say that 10 only has one significant figure. 104 has a 0 that is sandwiched between a 1 and a 4, and therefore that makes that 0 significant. So we would say that it has 3 significant figures. This 140 has this 0 at the end, and there are no decimal spots. Therefore, this 140 only has 2 significant figures, the 1 and the 4. The 1401 has 4 significant figures, and the reason is that the 0 is being sandwiched between the 4 and the 1. 1001. This is probably an interesting example because we have 2 zeros here. Now I want to make you guys aware that we are not using one of these zeros to sandwich the other one. Instead, it doesn't matter how many zeros you have, as long as there are 2 whole numbers somewhere in between them, they are all significant. And because we have a 1 at the beginning and a 1 at the end, these zeros are all significant. Lastly, we have 1100. So 1100 has 2 zeros at the end, and there are no decimal points. Therefore, only the 2 ones are significant, and so we have 2 sig figs. The next rule, trailing zeros are only significant if the number has a decimal. So what I just said a moment ago. 10, in the same case as the first example, or the example we went over last, has only 1 significant figure. 100, only 1 significant figure, since those zeros at the end don't have a decimal, and there are no numbers to the right of them. They're not being sandwiched, so neither are significant. Next, we have the 10.1. Now, we do have a decimal here, or 10.01. I did not mean to say 1. Apologies. So 10 with a decimal. The decimal is sort of acting as our sandwich here, and it's sandwiching the 0 between a 1 and a decimal, so it immediately becomes significant. Note here that we have a trailing 0, but in my rule I say trailing zeros are only significant if the number has a decimal, and it does have a decimal. Therefore, all of these zeros are significant, and we must include them. So there are 3 sig figs. In this case, we have 4 sig figs because, again, we have zeros being sandwiched by the decimal, and we have zeros to the right of the decimal. Next, we have this number right here, and we sort of have a combination of all the cases. We have a 0 being sandwiched by a 5 and a 4 and a decimal, and we have a 0 that is trailing, but because there is a decimal, it also is significant. All of these digits in this number are significant. And the same holds true for this number. Every one of these digits are significant. This trailing 0 occurs here, and there is a decimal, therefore it is significant. This 0 is sandwiched between the 8 and the 1, therefore it is significant, and all of these numbers are significant. We have 7 sig figs here. Next, we have leading zeros. Leading zeros are never significant. Leading zeros are what we get when we measure things that are very small. We should think of the leading zeros as nothing more than placeholders. In our first example, we have 15. So nothing new here, 2 sig figs. Then we have 13.10. So here we have 4 sig figs, nothing new. We have a trailing 0. And this trailing 0 is coupled with a decimal, therefore it is significant. Here we have our first leading 0, the 0 that comes at the beginning. This 0 is not significant. We are only caring about these 3 numbers here, the 3, the 4, and the 5. And here we have these 2 zeros that are leading, but we also have a 0 that's sandwiched between the 3 and the 4. The 0 that is sandwiched is significant, but the leading zeros are not significant. And finally, we have this value right here. We have these 2 leading zeros. We also have a 0 that's sandwiched, and we also have a 0 that's trailing. So the sandwiched 0 is counted because, well, it's between 2 whole numbers. And the trailing 0 is also counted because there is a decimal place in this number. So we have the 3, the 0, the 4, and the 0 as all significant. So 4 significant figures here. So these are the only rules that we have to take into account, really, when we are looking at a number to determine how many significant figures that number possesses. Let's go over addition. add, subtract. Add and subtract sig figs. I should note that the operation of addition and subtraction is a bit more involved than the operation of multiplication and division. It's a little bit more confusing too, but as long as you follow the rules, it should be pretty straightforward. So here are a list of steps that you should perform. Line up the decimal places. Two. Determine which number has the least decimal precision. Let's abbreviate this DP. 3. Place line to the right of the least right of the last sig fig on the number with the least decimal precision. Then after that, add, subtract, and then finally round. So these are the 5 steps that you'll need to solve pretty much any addition or subtraction of any numbers using sig figs. So let's do a few examples. Call this 1. Let's say we have 1.356 plus 11.3. Well, the first thing we want to do is we want to line up our decimal places. So we'll put 1.356 and 11.3 as such. So our decimal places are lined up. Next thing we want to do is to determine our number with the least decimal precision. And actually, I meant to show you what that meant right here. So let's pull this down. Say decimal precision. So let's say we have 0, 0, 0. Decimal point right here. So let's say that this was a number or some or a display on some what we would say is this is 1 decimal precision. This is 2 decimal precision. 3, 4, 5, 6. So if our number, for instance, had 0.12345 it would have 6 decimal precision. So this number right here would have 6 decimal precision. 0.12345, 0.1234, 0.123, etc., etc. So 5, 4, 3. We're essentially counting how many digits to the right of the decimal, and that will give us our decimal precision. Now there's also another possibility, so I will give you that as well. Let's say we have 1. Well, 1 has 0 decimal precision. So 1 has 0 dp. Let's say we have 10. So 10 has negative 1 dp, and so on and so forth. But let's say we had 11. This 11 would have 0 dp. Essentially, as we add stuff to the left, as long as this first digit is there, it still is 0 dp. However, if this first digit is a 0, then we would have negative 1. So 1, 1, 1, 1, 0, 0. This would be negative 2 dp, and so on and so forth. So this, it's not too important. It's just more useful when imagining something being being able to determine something's decimal precision. Normally, we would not use whole numbers for this, but to sort of be exhaustive in this list for this idea, I want to give you a way to calculate decimal precision for whole numbers that do not have decimal places. So we could use this concept of a negative decimal precision based on how many points to the left before we find our first non-zero digit. So let's get back to this example. The first step was to line up our decimal points, which we did. The second step was to determine which of these numbers had the least decimal precision. This has 1 dp, so it has a decimal precision of 1. This has a decimal precision of 3. So our least precise number is this 11.3. And as a result, we are going to use it for the next step, which was write a line to the right of the least significant figure on the number that is has the least decimal precision. So we find this 3 here. We go to the right of the 3, and we draw a line straight down like such. After we draw that line, we can perform our math. We should get 12.656. The next step is to look at this 6. It's the rounding step. So we look at this 6. We look at the number that occurs to the right of the line that we drew. We see that it's a 5. If it is a 5 or greater, we round the number up. If it is not, we keep the number what it is. And since 5 is indeed 5 or greater, this turns into 12.7. So 12.7 would be the answer for this example. Go to the next. So number 2, 9.568 plus 10. So first step is to line up our decimals. So we have 9.568, 10. Now, although there's no decimal in this 10, we know that the decimal place would be to the right of the 0. We won't draw it, though, because if we did, it would mean that this 0 is significant, and it is not. So, which of these numbers has the least decimal precision? This number has a decimal precision of 3. And this number has a decimal precision of negative 1. So this 10 has the least decimal precision. So we're going to use this 10 to draw our line. We will draw it to the right of the last significant figure. And the 0 is not significant, but the 1 is. So we will draw our line to the right of the 1. And then perform our mathematics. So we should get, let's see, 1,9,568. So at this point, we look at the 1. We look to the right of the 1. We see it's a 9. 9 is indeed 5 or greater, so the 1 gets rounded to a 2, and our answer would be 20. So this one is sort of interesting. I think it's the next one after. This is 3. Let's say we have 100, and we want to add it to 13.5. So first step, line up our decimal places. So 100. So I am failing here. Here we have everything lined up. We see this 100 has a decimal precision of -2. And we see that this 13.5 has a decimal precision of 1. So the 100 is the least decimal, has the least decimal precision. The last significant figure, or the only significant figure in the 100 is the 1. So we're going to draw a line to the right of that. And then we will carry out our addition. So we get 1, 1, 3.5. Look at the 1. Go to the right of the 1. We see that the 1 is not 5 or greater. So we round up. Or we don't round up at all. So this 1 stays a 1. And we get a final answer of 100. This is an interesting equation because we see that adding the 13.5 to the 100 did not change its value at all, which under normal circumstances would be like, what? That can't be right. But indeed, it is right. What this is telling us, what significant figures is telling us, is that the 100 is so bad of a measure that the 13.5 has no significance of being added to it, because that 100 could be off by a factor of 100. And that factor is so great, it's greater than the value that's being added to it. And since that's the case, adding that value to something that could be off by more than what the value that it's being added to, it's pointless to add it. And as a result, we get a 100 back from our work. This is what significant figures are doing. This is what this mathematical operation is doing. It is allowing us to truncate and round numbers to the least precise of the values that we are given. Let's do this final one. 4. We have 3.542. We're going to subtract from 2.1. So let's align our decimal spots. 3.542, 2.1. We see that the 2.1 has 1 decimal precision. We see that the 3.542 has 3 decimal precision. So we are going to use the 2.1. We look to the right of the 1, and we draw our line because the 1 is the last significant figure in 2.1. And then we perform our math. It should give us 1.442. Now we look at the 4 because it's to the left of this line. Then we look at the number to the right of it, which is 4, which is not 5 or greater. And as a result, we do not need to round anything. So our final value for this equation should come out to 1.4. And this is pretty much everything for the addition and subtraction of polynomials. This is, I would say, quite a bit, not quite a bit, but a little bit more difficult than multiplication and division. Multiplication and division is much quicker and much simpler. So, mult, div, sig figs. So the multiplication and division of significant figures. So let's say we had the number 8.4. And to that, we were going to not add, we're going to multiply 5. If we plug this in a calculator, we'll get the value 42 out. What we want to do for the multiplication and division of sig figs is to round our final answer so that it has the same number of sig figs as our least, or our number that has the least number of sig figs in our operation. So what I mean is this 8.4 has 2 sig figs, this 5 has 1 sig fig, and this 42 has 2 sig figs. We need to make this 42 have 1 sig fig, so how are we going to do that? Well, we're going to round it. And when we round it, we get the value of, so 42 will round to 40 to also get 1 sig fig, and that's all we need to do. That's quite literally it. To a few more. So let's say 279 multiplied by 83. 279 has 3 sig figs. 83 has 2 sig figs. That will mean we need to round our answer to 2 sig figs once we get it. When we perform this multiplication, we get 2, 3, 1, 5, 7. We need it to have 2 sig figs, so 1, 2. We look to the right of that 3, which is a 1, so we don't need to round that 3. And this becomes 23,000. The same way, if we wanted 1 sig fig, we look to 4, we look to the right of the 4, we see it's a 2. The 2 is not greater than 5, so we don't round. That is the only examples I want to give for multiplication and division, because it really is that simple. You literally count the number of sig figs that you are starting with. Whichever number has the least amount will be what you round your final answer to. This last portion of significant figures I want to talk about before we get into the sort of chemistry-based stuff is probably the trickiest portion, and it is known as mixed operations. So let's say we had 100 plus 3.54 divided by 0.9. So what we want to do is break this into parts. It's important that we know order of operations for these. So because we have an addition operation and a multiplication operation, we are going to perform the, or not multiplication, division. We are going to perform the division first, and then we are going to perform the addition second. So this division, when we perform it, will give us the following number: 3.89010989. The reason I'm writing all these digits out is because it is very, very important that you do not introduce rounding errors when we perform multi-step operations like this. When you perform these multi-step operations, what is going to happen is we are going to get a value out of one of these operations, and then we might need to do something to this value before we move forward with it. And what I mean is, this 3.54 has 3 significant figures, and this 0.91 has 2 significant figures. That would mean that if this was the only operation that we performed, if this addition wasn't there, our final answer would need to have 2 significant figures, and it would be the 3 and the 8. However, we do not want to perform the rounding of this number into 3.9 and then add this 100. The reason is we will introduce the thing called rounding errors. Instead, what we want to do is to include this entire number here, but either write out or in your head, remember that these numbers that I'm drawing a box around have 2 significant figures. No. These numbers that I'm drawing a box around are not significant. This is the only important part of this multi-step operation. Whenever you do this, we want to determine from each operation how many significant figures are being carried for the next operation. We would then take this value right here and add the 100 to it. We would then have the 100 plus this. So let's do that. We would have 100 plus 3.8. 89. Let me actually copy it. So we're lining up our decimals. Because this is addition and subtraction, we need to line up our decimals. We will now look at our least decimal precise number. This is where drawing that box comes becomes very important. This number right here only, even though it has all these extra numbers tacked onto it, remember we're supposed to imagine that these numbers aren't there or they're not included. We only have this 3 and the 8. So based on this, we would say that this has 1 decimal precision. This number has -2 decimal precision. This number 100 is the least decimal precise number, and so we will use it to draw our line. We look at the least significant figure in that number, and that is the 1, and we will draw a line to the right of it. We then perform our mathematics, which gives us 103.8901098. Look at the 1. Look to the right of the 1, it's 0, so it doesn't get rounded, and as a result, our final answer would be 100. Notice how we didn't gain anything. That's an interesting sort of thing to take into account. Let's look at another one. Let me see if I can have one that actually forces it. All right, this will do. This will be the last example of this. This one will work pretty well for it. So let's say we have the following number: 100 point. Add to 0.91. Note how it's pretty much exactly the same as the first one, with the exception is I added a decimal point and I put a whole bunch of trailing zeros. So what happened is this number now has 6 significant figures. 6 significant figures, and it also has 3 points of decimal precision. We have 3 sig figs here. We have 2 sig figs here. We have 2 points of decimal precision, and we have 2 points of decimal precision. When we perform this operation right here, we will get the exact same thing that we did before. So I'll do that. Now, when we do this next step, we're going to get something a little different. Plus 0.000. So now what we are going to do is we are going to look at the least decimal precise number. This has 1 decimal precision. And this has 3 decimal precision. So the least decimal precise number this time is the 3.8901099. In the previous example, it was the 100, but when we attacked on those extra zeros with the decimal point, we changed things. So this is actually going to change how this answer is going, the answer that we're going to get. So instead of putting the truncation mark here like we did, we are going to look at the 3.890. We are going to put it to the right of the least significant digit. This is where the box comes into play. It's actually, this doesn't mess. actually make this look like 100. So this time we're going to look at the 3.8. The last significant digit is the 8, so we're going to draw a line to the right of the 8. And now we are going to perform our math. And we will get, well, we're going to get the exact same number that we got last time, which is 103. 8 9 0 1 0 9 8 9. But note that our line is in a different spot. We will look at the 8. We will see that the number to the right of the 8 is a 9, so that 8 will be rounded to a 9, and our final value will be 103.9. Notice how we have a different value just by tacking on a few zeros and a decimal place to one of our numbers. So we have 100 here, we have 103.9 here. So the main thing that you need to keep into account is when we perform an operation in a multi-step problem like this, do not round until the very end. Every time you perform an operation, write down somewhere which of the digits are significant and which are not significant, like I did right here with this blue box. Then carry forward with whatever operation you need to do. Let's talk about accuracy and precision now. So accuracy and precision is pretty much always described like this picture that I'm about to copy over that probably won't copy over. Oh, I didn't want to copy over. I really hate Microsoft OneNote. It just fails so often. It's not going to copy any of my pictures. See if I can copy them one. Nope, can't even copy them one. It's refusing to copy the images that I want to pull over, and I really don't want to draw them again. Looks like I will have to draw them again. Startboard. All right, let's say I have these 3 dartboards. Let's throw some darts in them. So let's say, I don't want. Let's say I put a dot there, a dot there, a dot there, and a dot there. They're all really close together and they're all on the bullseye. Let's say I put a dot here, 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 and let's say I put a dot. They're all sort of hugging the bullseye, but they're scattered. Let's say that I put a whole bunch of dots there. They're all together, but they're really far away from the bullseye. Finally, let's do this final example. Just gonna put them everywhere. There's no real organization on them. They're just completely randomly dispersed throughout. Let's see if this will copy. It's not going to scale it, are they? Nope. Fortunate. All right. I will have to write everything. So this would be what would be considered high accuracy, high precision. This would be considered high accuracy. Low precision. This would be considered low accuracy. High precision. And this would be considered low accuracy, low precision. Low precision. So the next thing we could do is let's look at some numbers. This copies. That's a little large. Let's see if we. So these are in the same order that I have these. Let me just copy paste. This is high accuracy, high precision. This is high accuracy, low precision. This is low accuracy, high precision. This is low accuracy, low precision. So let's look at these. So we take a 5-gram weight and we place it on a scale 5 separate times, and we get the following masses each time. So the scale is going to give us a slightly different answer every time. We get 5.01, 4. You could all receive this. And as a result, you can see that the numbers are very, very close together, and they are also very, very close to that 5. So we could say that they are high accuracy and high precision. We do the same exact thing, and we get the following masses. We get these masses. We see that if we take these masses and do an average, the average of them actually come very close to 5. So whenever you have numbers that sort of wrap around the ideal number that you want, although they might be a little dispersed, we can still consider that as a high accuracy set of numbers. Now, the precision, on the other hand, is low. And the reason the precision is low is because the numbers are not within agreeance of one another, or they're not within a very close proximity to one another. In this third example, we see that all of our numbers are very close together, but they're very far from the actual value of 5. And so we would say that this has a low accuracy because it's far from the actual value. But because they're very close together to one another, they're high precision. And finally, we look at this last set of numbers where we have low accuracy and low precision. And we can see that essentially the numbers are all over the place. They're not close to one another, nor are they close to any other value. So this would be honestly the worst case, and this would be your best case. High accuracy, high precision. Now, high accuracy, low precision is not actually that great, but it's all right. And low accuracy, high precision is not all that bad either, because usually this would be indicative of some sort of systemic error. So we would have the same error constantly happening all the time, and if we knew how much this value varied from the actual value, we could perform some sort of, or add some sort of mathematical constant to correct it. So this is the worst case when you have low accuracy and low precision. When you have low accuracy and high precision, you could sometimes do something about it, and the same thing with high accuracy and low precision. Now that we are done talking about numbers, we are done talking about significant figures, we will talk about something chemistry related, and that will be the entire discussion for today. So we will now talk about what is known as concentration. So in order to define concentration, I need to define 3 terms that you may or may not be familiar with. We have solvent, we have solute, and we have solution. Now, the solvent, by definition, is the thing in most abundance. So by that I mean usually when you put something in water, dissolve it in water, the solvent is water, and water is obviously the thing that's in most abundance. If it wasn't the thing in most abundance, it would not be the thing doing the solvating. The solute is the thing that is being solvated by the solvent. So, how should I put it? Solvated by the solvent. And we could think of solvated as sort of like dissolved, although in chemistry we don't use the term dissolve, we use the term solvated. So a solvent solvates a solute. I know it's a lot of S words, but that's the proper way of saying it. Our solvent is the thing that's in most abundance. The solute is the thing that the solvent is going to take into itself. And the solution is the solvent plus the solute. So this is super important. Make sure you have these terms memorized and could sort of understand what they are. The solution would be the entire container of everything together. So if I took a beaker and I filled it with water and then I added salt to the beaker and I mixed it up, the contents of the beaker would be considered the solution, the water in the beaker would be considered the solvent, and the salt that I added to that water would be considered the solute. So this is the primary thing that we are going to discuss for the remainder of this lecture. We're going to talk about how we could use these 3 things to define what is known in concentration in several different ways. So here are the following terms that we use for concentration. We have ppm. We have ppb. We have big M. We have little m. We have what's known as weight percent. And finally, we have what's known as volume percent. So the idea is that at the end of this lecture, you should be able to calculate for any of these values as well as convert between them. So part ppm stands for parts per million. ppb stands for parts per billion. Big M stands for molarity. Little m stands for molality. Weight percent stands for weight percent. And volume percent stands for volume percent. Here are the equations for each of these. We will have grams of solute over grams of solution. And we're going to multiply that by 10 to the 6th. Next, we have parts per billion, which is essentially the exact same thing. Instead of being multiplied by 10 to the negative 6th, though, we are going to multiply it by 10 to the 9th. Parts per million and parts per billion are a way of essentially describing very, very, very small concentrations in substances. So essentially, when we divide that solute by the solution, we're going to get a very, very, very small number. And if we multiply it by 10 to the 6th or 10 to the 9th, the number will become more manageable and more easily read. And then we could attach the parts per million or parts per billion piece to it. And it will be the unit attached to that number. Next, we have molarity, which is essentially moles of solute over liters of solution. This one should be a familiar one for you. Molarity is something that I'm hoping that you are all very familiar with. Be using it quite a bit. Molality, something that's not used quite often. That's not used often is moles of solute over kilograms of solution, or solvent rather. So just make the note here. Molality is sort of strange compared to the other ones. Instead of being divided by the solution, it's being divided by the solvent. Weight percent is essentially grams of, actually right here, is grams of solute divided by grams of solution multiplied by 100. And volume percent, very similar. Instead of grams, it's volume. So these are all the formulas that you need to know for essentially doing any sort of concentration calculation. So I would not say necessarily you need to memorize them, but definitely be familiar with them. So let's actually use them. Let's do our first problem. Let's do weight percent to molarity. We're going to do several different values here. Let's say we have 10 weight percent HCl. Let's say we have 20 weight percent HCl. Let's say we have 30 weight percent HCl. So here are our HCl values. When we are doing weight percent, the thing that we also need to know is the density of whatever our solution is. So whenever we're doing these types of problems, make sure that you also know the density. Density is represented by phi, and phi for HCl, the density of HCl, is equivalent to 1.19 grams per milliliter. Remember, density is a measure of how much stuff could fit into how much space. Space is measured by milliliters, and stuff is measured by grams. So we're measuring how much stuff could fit in a milliliter, and we're saying that 1.19 grams could fit in a milliliter for HCl. So now that we have the density of HCl, we could say the following. If in weight percent, first calculate the mass in 1 liter solution. So in a lot of these problems, we're going to be making some sort of initial assumption. And in this assumption, we're going to assume that we have a liter of this substance. And if we have a liter of this substance, it weighs 1.19 grams per milliliter. If we had a liter of it, well, a liter of it would weigh 1,190 grams. 1 liter, 100% HCl. So we now know that if we have 100% HCl, how many grams it weighs. And at this point, you may sort of be figuring out where I'm getting at or not. We now just need to figure out what if we have 10%, 20%, and 30%. And it truly is that simple. So let's say with 10 weight percent, that would equal 0.10. Let's actually not do this. Let's do 10, 20, 30. We are going to take this 1,190 and we are going to multiply it by the appropriate percent. So this should be 0.1, this should be 0.2, should be 0.3. Because remember, if we are going to calculate the percentage of something, we need to convert it from its percent form, which is what it is in here, to its decimal equivalent. So we are essentially converting to its decimal equivalent form. So we can multiply by 1,190. We will get 119, 238, and 357 grams. So at this point, we know that 10% of the entire bottle would weigh 119, 20% of the entire bottle would weigh 238, and 30% of the entire bottle would weigh 357. We now actually have the mass of HCl that is in each of these bottles. And if we have the mass of HCl, well, we could determine how many moles of HCl by using a very simple formula by using the molar mass of each of these compounds. So let's write this down. All right. So now that we have grams of solute and volume of solution, we can calculate molarity. But first, let's take all of these values. And now let's use the molar mass. So HCl has a molar mass of 36.455 grams per mole. So if we divide each of these by 36.55 grams in 1 mole, we will get the following values. 3.264, 3.264, 6.529, and 9.79. This would be moles of HCl. Now, the last thing we need to do is to convert this moles into molarity, which is actually crazy easy because we made the assumption that we were dealing with 1 liter of solution. And if you remember that molarity is equivalent to moles over liters, because we have a 1 per liter, the molarity essentially becomes the moles. So we will get, for each of these, values. One final thing we need to do, and that is to account for significant figures. Our initial question had our weight percents with 1 significant figure, 10, 20, and 30, only 1 significant figure. And because the only operation that we are performing here are multiplication and division, we do not need to care about doing any of that truncating. We don't need to do any sort of lines or aligning anything. We simply need to round our final answer to have 1 decimal. And so what we are going to do is we will say that this is, let's just remove, this will be 7. This will be 3. And this will be 10. Here are our final concentrations for each of these weight percents based on the numbers that we have. So 10 weight percent is 3 molar, 20 weight percent is 7 molar, and 30 weight percent is 10 molar. All right, let's move to the next part. So we're going to do the same thing, but this time we're going to use volume percent. So volume percent similarity. Let's say we have 10 volume percent HCl. Let's say we have 20 volume percent HCl, and let's say we have 30 volume percent HCl. This time we're going to put a decimal. We could make that 0 a significant digit, and now we will perform our work. We also know that the density is the same, so HCl 1.19 grams per milliliter. So we're going to essentially do the exact same thing, but it's actually a little bit easier. What we are going to do is essentially we know density. We are going to say that at a density of 100 milliliters, down, make assumption. Let me actually just copy the whole sentence I wrote down from the first one, since it's the exact same thing we're going to do. Writing it our way. Did I not write it? Assume that we have 1 milliliter. No, I didn't write it. So assume 1 liter. So if we assume 1 liter, that would mean that each of these are 10% by volume. What's 10% of a liter? Or not 10%, 10%, 20%, 30%. It essentially is going to come out to 10% of 1 liter is 100 milliliters. 20% of a liter is 200 milliliters. And 30% is 300 milliliters. So this is a little bit simpler with volume percent. We could essentially use the volume percents to go right to the equivalent volume. And now, instead of going in the way where we used density to get to volume, we are going to use the density to get to mass this time. Remember, we need to figure out the math of the amount of the HCl that's in each of these containers. So if we have 100 milliliters of HCl, that would mean that it has a density of 1 milliliter for every 1.19 gram. Actually, just copy this completely over 3 times. And this is going to equal the following: 119, 238, and 357. Next thing we want to do is we essentially are going to take these grams and we are going to convert into moles. So I actually think this problem is going to grind out. Yes, it is. It just so happens that this problem is going to grind out the exact same as the previous problem. So we have the same masses based on these volumes and using the densities. So we're going to take the 119 grams and convert it into moles. And then when we divide by our volume, so now that we are in moles to molarity, we essentially are going to divide by 1 liter again. But again, since we are dividing by 1 liter, we're dividing by 1. So this molarity, or this mole value, becomes the molarity. So instead of moles of HCl, this is the molarity of the HCl. One more thing down. Pull it down because I didn't write it. So we would say 10, 20, 30 volume percent, decimal point here, would equal, we just need to truncate these values. Well, we have 2 decimal places here in each of these instead of 1. So this 3.2 becomes a 3.3. .3, 6.0 5 and 9.8 molar. So here would be the final answer here. It's very similar to the process from going volume percent to molarity as is weight percent. And I should also note that it just so happened that our values came out to be very close. They're pretty much the same. However, I will say that that more or less just happens to be to chance. Just note that. So this is essentially how we do volume and weight percent. What else do we want? All right. I'm almost done. I just want to talk about parts per million. And then we're going to do one dilution problem, and that will be the last thing we talk about. So let's do parts per million. Molarity. So let's say we have 105. ppm of chlorine. Let's say we have 205 ppm of chlorine. And let's say we have 305 ppm. So ppm, when we look at it, is equivalent to grams of solute over grams of solution times 10 to the 6th power. Another way we could look at it is 1 milligram over 1 liter. Now, I want to note that this is for H2O. We could make this assumption because water has a density of 1 gram per liter at room temperature, and therefore we know that the liters and the mass are the same. So if we wanted to, instead of saying 1 liter, we could say 1 milligram over 1,000 grams. And then finally, we could say 0.001 grams over 1,000 grams H2O. So what's going on here is you'll notice that these two numbers are separated by a distance of 1,000,000. And this is where the ppm comes into play. Whenever we are dealing with ppm, we are almost always going to be dealing with something in an aqueous solution, so water. And so you could almost always use this assumption right here to essentially determine what the ppm is using this assumption. So what we would say is 105 ppm is the same as 105 milligrams over 1 liter. So there are 105 milligrams in 1 liter for 105 ppm. 205 ppm equals, well, 205 milligrams over liter. And 305 ppm equals 305 milligrams per liter. So this is actually much easier than you would think. As long as we make this, make this assumption right here that 1 milligram per liter is what essentially a ppm is, we very, very, very easily are able to convert ppms into a mass equivalent. And once we get the mass of something, we know we could get the molarity of it by essentially converting the mass into moles and then dividing by liters. And as you know, we have mass, we have liters, so all we need to do is take these milligrams and convert them into, well, their appropriate number of moles. So let's do that. So let's say 105 milligrams. We'll say 205 milligrams. And we will say 305 milligrams. What this is equated to is 0.00. A little bit of is equivalent to 105, 205, and 30 grams. So here we have our mass from milligrams into grams using just a basic conversion of pulling this decimal 3 points to the left. So we went from milli to the base unit using that metric system. So now we have our mass in grams. We know that we could look up at the molar mass of chlorine, and chlorine has a molar mass of 5.453 grams per mole. So this is what we want to do. We want to get rid of grams and we want to go to moles. So 1 mole on top, and we put 35.453 grams on bottom. And we will do this for every one of these. This will give us the answers of, very small answers, 0.00296, 0.00578, and 0.00860. So here we have the moles of Cl. All we need to do is to find the molar mass, or the molarity now. And since we know that the volume is 1 liter, 1 liter, 1 liter, we get 0.00296 moles, 0.00578 moles, and 0.00860. Not moles, molarity. And here would be our final answer for this problem. We converted the ppm into molarity by making this first assumption, converting the milligrams into grams, and then going from grams to moles and dividing by the 1 liter that we got from our initial setup. This is how we do pretty much all of these problems. I want to make one note here for parts per billion, and then we will move on to the last part that we will talk today. So parts per billion is exactly the same as this, except it's and to the 6, it's 10 to the 9th. And instead of milligrams, well, micrograms. And so this is the only difference here. We will use this assumption instead of the previous assumption when we do parts per billion. Because when we do micrograms, we get 0.0000001 gram to 1,000 liters. Milliliters. And that's the same as grams for water. So you could see that the difference between these two numbers is a billion apart. That's where the billion and parts per billion comes from. So when we do parts per billion, if you ever need to use parts per billion, make this assumption where we use micrograms over liters. And when we use parts per million, we use milligrams over liters. Just keep that in mind. So it'll save you guys a lot of time and frustration. Finally, I'm going to introduce you to the dilution formula. So the dilution formula is C1 times V1 equals C2 times V2. The book may use a different letter than I'm using. Some texts use different letters than I'm using. I like these letters because I think when I see C, I think concentration. When I see V, I think volume, and that's exactly what they stand for. So C1 is stack concentration. Let's say V1 is the equivalent volume required. C2 is going to be final concentration. So this is the concentration that we are trying to get. And V2 is going to be final volume. Now, in this equation, it will most likely be V1 that we are solving for. So this equation, for most purposes, we are going to have it as V1 is equivalent to C2 times V2 all over C1. So if we have it set up like this, we are able to determine how much volume we need to pull from a stack solution of a known concentration to be diluted to the concentration we want to reach. So let's do a problem. Let's say that we have a 44 weight percent solution of ammonia, and we want to bring it to 0.100 molars at 100 milliliters. So we want 100 milliliters to be at this concentration, and this is our stack concentration. So stack concentration, this is going to be our final, actually, let's write this all down. Our final concentration is going to be C2. This is going to be V2. This is going to be C1. So notice how we are only looking for V1 as I have set up originally. Now, because this is in weight percent and it wants it in molarity, we first need to convert to like terms. So we need to convert this weight percent to molarity. So this whole this is going to be a multi-step process. So we're going to go from weight percent, grams, from grams to moles, from moles to the molarity. So we need to figure out what this concentration of this solution is. And then we're going to go to our final concentration, which is this one. So we need to figure out what the initial concentration is in molarity from weight percent. And we do that by going from weight percent to grams, grams to moles, moles to molarity. And then we're going to use our dilution formula to go from the initial concentration that we have in our stack to our final concentration that we actually want. So let's start with 44. With 44 weight percent, NH3. So what we want to do is assume 1 liter. And if we have 1 liter of NH3, the density of NH3 is 0.899 grams per milliliter. What we want to do is at 1 liter, that would mean it would weigh 899 grams, 100% NH3. So now we want to figure out at 44%. So we're going to take 0.44. We're going to multiply it by 899. And we are going to get 395.56 grams of NH3. you were doing this in a calculator, I would suggest having your calculator constantly use the numbers that you are pumping out, so we won't introduce any sort of rounding errors. I'm keeping as many numbers as I feel like writing out, but ideally you would want to keep all of the numbers. So ideally you would want your calculator to do this all in one step, or to use your calculator's ability to pull a value from a previous equation into a new equation. That way we're not missing any numbers when we're doing the next step. So now that we have the grams of NH3, we need to go from grams of NH3 to moles of NH3. So NH3 has a molar mass of 17.031 grams. So we are going to take this 395.56 grams of NH3. We're going to multiply it by our molar mass, and our molar mass says the following. We want moles on top, and we want grams on bottom. So 17.031 grams. And that should, when we punch it out of a calculator, give us a value of 23.225 moles NH3. But if you recall, because this entire thing we assumed was 1 liter, we could also state that this is 23.225 molarity. So now we have our M1 right here. We're at this part. We just need to use M to go to M2, and to do that, we will be using this equation right here. We have all of our values. This is going to be our C1. Our C2 is going to be 0.100. Let's see, and our V2 is going to be 100. Now I want to make a note right here. It's fine that we leave this as 100 milliliters, even though that we are in molarity, and ideally we would sort of want to cancel out this 100 milliliters by converting it into liters, because molarity is 1 over liter. However, this equation right here is more or less a fraction that is going to give some relative value. And because of that, it does not matter that if you're in milliliters, as long as your volume 1 and volume 2 are going to be in the same units, you're totally fine of using whatever sort of volume you would like to use, as long as you are constant in your terms. So your C's will all be the same unit, and your V's will all be the same unit. So just keep that in mind. So we will now essentially plug everything into this equation, and we will get 0.100 multiplied by 0.100 divided by 23.225. That will give us a value of 0.4305 milliliters. We go back to our original question. Let's see, where's our original question? It has 2 significant figures for the 44%. It had 3 significant figures for this 0.100 molar, and it had 1 significant figure for the milliliters. Therefore, our final answer must have 1 significant figure. So this 4305 will become 0.4 milliliters. So what does this mean? This means that you are going to take 0.4 milliliters of stock. You're going to add it into what's known as a volumetric flask, and this volumetric flask is going to be 100 milliliters. Once you add it to the volumetric flask, your volumetric flask is going to essentially have chemical inside it. So let's make it. And then your volumetric flask is going to have some line or marking on it, and that's going to be the 100 milliliter marking. You are going to add H2O to this until you reach that marking. And then will have your desired concentration. Actually use green. Essentially, you're going to fill this entire thing up. And then our green stuff will essentially be dispersed evenly in it. And this will be what we are left with. This is our final product. So this is essentially all the steps that we would do in any sort of concentration dilution. We will use this formula right here, and we will manipulate it if we need to. But as long as we have our V's, or our volumes, in the same essential unit that we want, and we have our concentrations in our same unit that we want, we are free to use this equation as we please. Just note that we want our V's to be the same and our C's to be the same. So this will conclude everything that I want to talk about today. So other than that, we will speak next time.